All right, good day, everyone. Today we are going to be looking at a very important topic in chemistry, which is chemical thermodynamics. Now, what is chemical thermodynamics? The first we'll be looking at here. Now, thermodynamics, like chemical thermodynamics, is the study of it and its transfer or transformation. Now, we have some limitations of thermodynamics, like inability to test whether a reaction will be fast or slow. Thermochemistry is a branch of thermodynamics that deals with heat involved in chemical reactions. The laws that governs these thermodynamics are the first law, the second law, and the third law, and the zeroth law. Now, the zeroth law throws light on the thermal equilibrium between systems, which tells us that if system AB are separately thermal equilibrium with a third system, or if bodies AB are separately thermal equilibrium with a third body C, therefore bodies A and B are also in thermal equilibrium. That is zeroth law of thermodynamics. Throws light on thermal equilibrium between systems. Now, two bodies are said to be in thermal equilibrium if and only if their temperature is the same thing. The first law of thermodynamics tells us that it speaks on the eternal energy of a system, and it follows the law of conservation of energy, that energy can neither be created nor destroyed. We can transform from one form to another. So it deals with the internal energy of a system, while the second law tells us that the entropy of an isolated system always increases. And also talks about the irreversibility of natural processes, and correspond actually also with the closure statement that heat cannot spontaneously flow from the area of colder region to higher region. We have the third law, which tells us that if the temperature of a system reduces to its absolute zero, the entropy will reduce to its constant value. To its what? Constant value. So that law talks more about absolute zero entropy. When the temperature of a system reduces to its minimum, to its absolute zero, the entropy of that system will reduce drastically to its constant value. Now, a system is any part of the universe chosen for thermodynamic studies. So what we mean by system is any part of the universe chosen for thermodynamic studies. The boundary is that which is acting as a separate between the system and the surrounding, while the surrounding is the part which is external to a thermodynamic system. Thermodynamic universe, you are seeing here, is that which encloses the system, the surrounding, and the boundary. Now, a system can either be isolated, opened, or closed. So thermodynamic system can either be open system, closed system, or isolated system. Now, a system is described as an open system if it allows the flow of matter and energy across its boundary. Otherwise, we term it as closed system if it allows only the flow of matter, if it allows only the flow of energy, but not matter. So a closed system is a system which allows only the flow of what? Energy, but not what? Matter. Isolated system is a type of system that don't allow the flow of matter, neither energy. So most like open bottle, open baker, open anything open, it we eventually act as an open system. Most of the things that are opened eventually act as an open system unless otherwise. While most of the things closed will be acting as a closed system. If and only if energy can cross its boundary, but not the matter inside or the substance inside. Now, the major example or a likely example of isolated system is a thermoflask, because the thermoflask can hold heat energy for some period of time. But in per se, since heat can still flow across its boundary, we can also classify it as a closed system, because an isolated system is a system that don't allow the flow of either matter or energy across its boundary. Now, all right, this system we're talking about has some properties. Use the properties of a thermodynamic system. Now, the properties can either be intensive properties or extensive property. So we have the intensive properties, we also have the extensive properties. Sometimes they do term intensive as also specific. Now, intensive properties are those properties of a system that do not depend on the amount of substance present in the system. Now, a system that will not depend, the property of a system which will not depend on the amount of substance present in that system is called intensive property. Example can be temperature, color. Boiling point is also intensive property. While extensive property is the property of a system that depends on the amount of substance present in that system, like volume, entropy, etc. All right, we have thermodynamic functions. Now, the functions I will be discussing here are the state functions and path functions. Now, what is the meaning of state functions? Now, state functions are those functions whose initial and final value do not depend on the path followed to arrive at them. The initial and final value do not what? Depends on the path follows to what? To arrive at them. Example, they can be density and so on. Pressure, they are state functions because their initial and final value will not depend on the path follows to get them. While path functions are functions whose initial and final value depend on the path follows. We also call them non-state functions. Now, major examples of these path functions or non-state function are the heat and work. Heat and work. So take note of that, very, very important. The difference between state functions and path functions. State function is a function whose initial and final value depend on the path, do not depend on the path follows to arrive at them. While path functions, initial and final values depend on the path follows to what? To arrive at them. We have some processes in thermodynamics like the isochoric process, adiabatic process, isobaric process, isothermal process. Now, I'm looking at these four processes now. The isochoric process is a process in which a system will undergo. At the end, the volume will remain constant. So the constant volume process or the process a system undergoes in which the volume will not change, the volume will remain constant, is called isochoric process. Adiabatic process is a process in which the system will undergoes and the heat will not change. It's a process at constant heat. Isobaric process is a process at constant pressure. A process the system will undergoes in which the pressure will not change. While isothermal process is a process a system will undergoes in which at the end of the day the temperature will not change. The constant temperature process is the isothermal process. Now, the first law of thermodynamics, which we have quoted before, which corresponds to the law of conservation of energy. Energy can neither be created or destroyed, so on, can be written mathematically as du is equals to q minus w, or du is equals to q plus w. Now, we can also use E in terms of U here. That is, if you wish to use E as your energy. This way now, this U is our energy, the Q is the heat content, while W is our work. Now, when is W negative and when is W positive? Now, our work W is negative if work is done by the system, and the W will be positive if work is done on the system. Please take note of that. It's very, very important. Q will be negative for exothermic reaction and will be positive for endothermic reaction. So take note of that. Very, very important. W will be negative when work is done by the system and will be positive when work is done on the system. Enthalpy change is equals to the heat content of the product minus the heat of reaction. So also take note of that. So the delta H you are seeing here is called enthalpy. Now take note of this. The work done in the expansion of a gas in a vacuum is always equal to 0. It's very, very important. Take note of that. Very, very, very important. Very, very important. Now let's look at introduction to heat. Let's look at introduction to heat. What is the meaning of heat? Now, heat can be defined as an energy, can be transferred from one place to another due to temperature difference. So it's an energy that brings about a sensation of warmth. Now, heat can be studied under heat capacity or specific heat capacity. Now, what is heat capacity? Heat capacity is the amount of heat required to raise the temperature of a body, either by 1 degree Celsius or by 1 Kelvin. The amount of heat required to raise the temperature of a body is called heat capacity. And it's defined as Cp is equals to Q over d theta, or Q is equals to Cp d theta. The theta is the change in temperature, which is final temperature minus initial temperature. Q is the heat, then Cp is the heat capacity. Now, what about specific heat capacity? Specific heat capacity is the quantity or amount of heat required to raise the temperature of a unit mass of a body, either by 1 degree Celsius or by 1 Kelvin. Now, the amount of heat required to raise the temperature of a unit mass. Now, for heat capacity, there is no mass. But for this, our specific capacity now, we are now measuring mass. And we are specifically about the mass we are talking about. The amount of heat required to raise the temperature of a unit mass of a body, either by 1 degree Celsius or by 1 Kelvin. Take note of that. Very, very important. So C is equal to Q over M change theta, or Q will be, this times this, MC change theta. Our C is the specific heat capacity, M is mass, and the theta is temperature. Now, if you equate this heat to this heat, you are going to equate this to this. Theta and the theta will cancel out. Therefore, our Cp will be equal to Mc. So this is the relationship between heat capacity and specific heat capacity. Also take note of that. Very, very important. Now, let's look at this question. It says calculate the quantity of heat required to raise the temperature of 10 grams of water from 20 degrees Celsius to 50 degrees Celsius. 20 degrees Celsius to 50 degrees Celsius. Now, the amount of water we are looking at now, the mass of water is 10 grams. And the specific heat capacity of water approximately is equal to 4,000 200 joules per kilogram per Kelvin. It's a constant value. SHE for water is approximately equal to this. Alright, the change temperature will be the final temperature minus the initial temperature, which is 50 minus 20, which gives us 30 degrees Celsius. So if you convert both of them to Kelvin, the change temperature will still be the same. That's why even though this one is in joules per kilogram per Kelvin, you can still use this to solve. Even though you move both of them to Kelvin, it will still be 30 degrees Celsius or Kelvin. Converting 10 grams to kilogram, we're going to have 10 divided by 1000 gives us 0.01 kilogram. So on substituting this into the formula Q is equal to MC change theta, we're going to have this give us 1260 joules or 1260 joules. Very, very important. Now also calculate for this as maybe classwork or assignment. The specific heat capacity. Okay, let's look at this. Take note of this. You can write it down. The specific heat of water is 4.184 joules per grams Kelvin. Is 4.184 joules per gram Kelvin. What is the heat capacity of 50 grams of water? I repeat the question again. The specific heat of water is 4.184 joules per grams Kelvin. What is the heat capacity of 50 grams of water? The answer I'm going to get to be approximately 209 joules per kilogram. Joules per Kelvin. 209 joules per Kelvin. Ensure you solve that question to get the answer. Also take note of this, that this class is just a little summary on chemical thermodynamics. I hope you have gotten something from the class. Also look at other important calculations that involve heat and work done by a system or the system, and also note that heat capacity depends on the mass, and specific capacity do not depend on mass. So if you are asked a question, which of these depends on mass of substance present in the system, heat capacity depends on mass, but specific heat capacity do not actually depends on mass. It's independent of mass. Please take note of that. It's also very important. Thank you.